the number of derangements of a group of n distinct objects um, actually is usually described as the hat check problem, in which you're given a situation of n hats left at a hat check window. People used to do that, if you can remember the old movies. And if they're returned, in how many ways can they be returned so that no one gets the correct hat? All right, so this deals with an ordering of the hats. So it's going to be a permutation of the hats. And what we're going to do is do complement thinking. So first, how many ways to return at least one correctly. And as we did with the one-to-one or onto functions, I'm going to go ahead and label sets using A's as we have typically done. And A will be the set of returns or orderings of the hats with hat I correct. And of course that includes those where hat J might be correct as well, but the one thing that is important, that hat I is correct. And so we're going to look at the union of these. So the one with at least one correct, set with at least one correct, is the union of all these, is A1, that's just an A, A1 union A2 union all the way out to AN. And so because it's a union, hat 1 or hat 2 or etc. or hat N is correct, then to count that we need to use inclusion exclusion as per usual. So the number of ways to order the hats so that one in particular is correct, A1 or hat 1 is correct, would be, first of all, make sure that hat I should be saying, hat I is in position I. So we fix hat I in position I, fix hat I, and order the others. And I'm going to put that above here. So the number of ways to fix hat I, well, that's one way. You just put hat I in the I position. But the others, there are n minus 1 of them, can be permuted in any way, can be ordered in any way. So we get n minus 1 factorial. And so the sum of the sizes of the sets individually will be n choose 1, the 1 meaning I'm going to fix the ith hat, whichever I is, times n minus 1 factorial. And then 2 of them at a time would be choose 2 of them, put them in the correct positions, and then permute the other n minus 2. And darn it, that'd be the sum of those. That's how many of the ways there are to do it. To fix any particular I and j, you'd fix I and j and then permute the other n minus 2 of them, but there's 2 ways to choose 2 to fix. And in general, well, let's do one more. A1 intersect A2 intersect A3 would be, the sum of those would be pick 3 to fix and then permute the remaining n minus 3, like so, etc. So that tells us that the union of these, where at least one is fixed, greater than or equal to 1 correct, would be equal to n1, n choose 1, n minus 1 factorial, minus n choose 2, n minus 2 factorial, plus minus, and it goes all the way out to the n. Let's see, they could all be correct, right? We could put them all in the correct positions here. And so I'm going to have to put a minus 1 to some power here. But how many ways are they all correct? Well, there's only one way to put them all in the correct order. So that would be 0 factorial are wrong, is really what that is, but that's a 1. That's 1. That number right there, 0 factorial, are the remaining 0 of them to order in any order. They're all in the right places, none left. So that's what we have right there. Now let's see the parity here. Again, like per usual, it seems like when I have a 1 here, I have a plus. When I have a 2 here and here, I have a minus. So it'll be minus n minus 1, because this number 0 is n minus n factorial. Right, so the 2 here with the minus 1 corresponds to the n here with the minus 1 to the n minus 1. So let's go ahead and scroll down to where we're going to write this down formally. That's what we have right there. A derangement in a formal way. Let me go back. Let me go back just a minute. So the answer here would be n factorial minus this number here. N choose 1, n minus 1 factorial, minus n choose 2 in the brackets here, n minus 2 factorial, plus minus out to minus 1 to the n minus 1 times 1, like so. And that is actually n choose